The last good day.
66 million years ago, on an ordinary Tuesday afternoon, a Troodon mother was teaching her chicks to hunt. She didn't know it was Tuesday, of course. She didn't know it was the Cretaceous period, or that her species had been evolving for over 100 million years. She didn't know that her brain, gram for gram, was the most sophisticated piece of biological machinery the planet had ever produced. And she certainly didn't know that in approximately 4 hours, a rock the size of Mount Everest would slam into what is now the Yucatan Peninsula at 45,000 miles per hour. And that everything she was, everything her species could have become, would be erased from the future of Earth. But here's the question that haunts paleontologists, evolutionary biologists, and anyone who's ever looked up at the stars and wondered if we're alone. What if that rock had missed? Not by much. The universe doesn't deal in much. Just a few thousand miles, a rounding error in cosmic terms, a slight gravitational wobble from Jupiter, a different angle of approach. The asteroid sails past Earth, becomes another anonymous piece of space debris, and continues its lonely journey through the void. And on that ordinary Tuesday afternoon, the Troodon mother finishes her lesson. Her chicks grow up. They have chicks of their own. In 66 million years of evolution, the same 66 million years that turned a small, shrew-like mammal into you, reading this right now, those years still happen. But they happen to them. This is not science fiction. This is not fantasy. This is a serious scientific thought experiment that has occupied some of the greatest minds in paleontology. And the conclusions they've reached are disturbing. Because the evidence suggests that dinosaurs weren't just on their way to intelligence, they were almost there.
Let's set the scene properly, because most people have a completely wrong picture of the late Cretaceous world. Forget the barren volcanic hellscape of cheap documentaries. Forget the constant warfare between massive predators. The world of 66 million years ago was, in many ways, more sophisticated than our own. The planet was warmer, significantly warmer. There were no polar ice caps. Sea levels were 300 feet higher than today, and shallow seas covered much of what is now the interior of continents. North America was split in two by the Western Interior Seaway, a warm, tropical ocean teeming with life. And on the lands that remained, evolution had been conducting an experiment in biological engineering that lasted over 160 million years. To put that number in perspective, the entire history of mammals as dominant land animals is 66 million years. Dinosaurs had already been the dominant life form for 2.5 times that long. They had survived mass extinctions, continental drift, climate catastrophes, and the evolution of flowering plants. They had diversified into thousands of species, occupying every ecological niche, from tiny insectivores to 100-ton herbivores. But here's what most people don't understand. By the late Cretaceous, dinosaurs weren't just surviving, they were accelerating. The last 30 million years of dinosaur evolution produced more biological innovation than the previous 100 million combined. Hadrosaurs developed complex social structures and vocal communication. Ceratopsians evolved elaborate display structures that suggest sophisticated mate selection, a hallmark of cognitive complexity. Pack hunting became common among theropods. And in one particular lineage, the Troodontids, something remarkable was happening. Brains were getting bigger. Much bigger. Faster than in any other dinosaur lineage. Faster, in fact, than in any lineage that had ever existed on Earth. Ask anyone to name a dinosaur,
and they'll say Tyrannosaurus rex, maybe Velociraptor, thanks to a certain film franchise. The scientifically literate might mention Spinosaurus or Giganotosaurus. Almost nobody says Troodon. And yet, if we're asking the question of what dinosaurs might have become, what civilization might have looked like if the asteroid had missed, Troodon is the only answer that matters. Discovered in 1855, Troodon was one of the first dinosaurs found in North America. For over a century, it was considered a minor player in the Cretaceous ecosystem. A small theropod, about 6 feet long, weighing maybe 100 pounds. Predatory, certainly. Bipedal, obviously. But nothing special. Then, in the 1980s, paleontologists started looking more carefully at Troodon skulls. And what they found changed everything. Relative to its body size, Troodon had the largest brain of any dinosaur ever discovered. Not just a little larger, dramatically larger. Its encephalization quotient, the standard measure of brain-to-body ratio used to estimate cognitive capacity, was 6 times higher than the average dinosaur. For comparison, the encephalization quotient of early primates, our own ancestors at the time of the dinosaur extinction, was roughly equivalent to Troodon's. Let that sink in. At the moment of the asteroid impact, there was a dinosaur walking the Earth with cognitive capacity comparable to our own ancestors. But brain size alone doesn't make intelligence. What makes Troodon truly remarkable is what that brain was connected to. Evolution doesn't build intelligence from scratch. It works with existing structures, modifying and repurposing what's already there. And Troodon had almost everything that intelligence requires. First, the hands. Troodon's forelimbs ended in 3-fingered hands with partially opposable digits. Not as sophisticated as primate hands, but capable of grasping, manipulating, and potentially using simple tools. The wrist bones show evidence of high mobility, the ability to rotate and flex in ways that most dinosaurs couldn't. Second, the eyes. Troodon had enormous, forward-facing eyes that provided stereoscopic vision. This isn't just useful for hunting, it's essential for fine manipulation of objects. You cannot thread a needle with eyes on the sides of your head. Troodon could potentially have done exactly that. Third, the posture. Unlike most theropods, which held their bodies horizontally, Troodon evidence suggests a more upright stance. The hip and spine structure allowed for a posture closer to vertical than any other dinosaur. This frees the hands for manipulation rather than balance. Fourth, the social structure. Fossil evidence indicates that Troodon lived in social groups, possibly family units. Multiple individuals have been found together, including adults with juveniles in apparent teaching contexts. Social learning is the engine of cultural evolution. It allows knowledge to accumulate across generations rather than dying with each individual. Fifth, and most remarkably, the parental care. Troodon nests show evidence of sophisticated brooding behavior. Adults sat on eggs in a specific pattern, rotating them for even heat distribution. This isn't instinct. It's too complex, too variable. It requires decision-making, problem-solving, intelligence. Put all of this together, and you have something unprecedented in the history of life on Earth. A non-mammalian lineage that had independently evolved almost every prerequisite for sapience. The question isn't whether Troodon could have become intelligent. The question is whether the asteroid gave them enough time.
Here's a number that should keep you up at night. 7 million years.
That's how long it took the human lineage to go from Sahelanthropus chadensis, a small-brained ape that may have occasionally walked upright, to Homo sapiens, builder of cities, splitter of atoms, sender of spacecraft to other worlds. 7 million years. In geological terms, that's nothing. It's a rounding error. It's the blink of an eye. And the troodontid lineage had been evolving for 60 million years before the asteroid hit. They had time. They had the raw materials. They had the selective pressures. The changing climate of the late Cretaceous would have rewarded flexibility, problem-solving, adaptability. So why weren't they already intelligent? Why wasn't there a Troodon civilization when the asteroid arrived? The answer might be that we're asking the wrong question, because intelligence isn't a single thing. It's not a light switch that flips from animal to sapient. It's a spectrum, a gradient, a long, slow climb up a mountain whose peak we can't even see. And Troodon might have been much further up that mountain than we give them credit for. Consider, we have almost no Troodon fossils from the very end of the Cretaceous. The species we call Troodon is actually known primarily from specimens dating to approximately 77 million years ago, 11 million years before the extinction. That's longer than the entire existence of the genus Homo. That's longer than the gap between us and the common ancestor we share with chimpanzees. What were troodontids doing in those final 11 million years? How much did they change? How much did they develop? We don't know. The fossil record is silent. But we can make educated guesses. And in 1982, one scientist decided to do exactly that. His name was Dale Russell, and his conclusions would become the most controversial and most intriguing thought experiment in the history of paleontology.
Russell was the curator of fossil vertebrates at the National Museum of Natural Sciences in Canada. He had spent decades studying dinosaur intelligence, particularly the troodontids. He had measured their brain cavities, analyzed their sensory capabilities, reconstructed their behavior from fragmentary evidence. And he asked himself a simple question. If the asteroid had missed, if troodontids had continued evolving for another 66 million years, what would they look like today? The answer he came up with would be called the Dinosauroid. It would be published in a peer-reviewed journal. It would be ridiculed by some scientists and praised by others. It would inspire decades of debate about the nature of intelligence, the predictability of evolution, and the probability of alien life. And it would raise a question so profound that most scientists still refuse to engage with it directly. Are humanoid civilizations inevitable? Is the shape of intelligent life predetermined by the laws of physics and biology? Or did we just get lucky? Because if Russell was right, if the Dinosauroid was a plausible outcome of continued saurian evolution, then the universe might be filled with beings that look remarkably like us. Not because they're related to us, but because intelligence itself has a shape. And that shape might be required. The Dinosauroid, Dale Russell's forbidden vision. In 1982, a scientific paper appeared in the journal Pelagius that would haunt paleontology for the next 4 decades. The paper itself was unremarkable in its formatting: dry academic prose, careful citations, measured language. But buried within its pages was an image that would escape the confines of peer review and burn itself into the collective imagination of an entire generation. It showed a creature standing upright, humanoid in posture, large-eyed, green-scaled, 3-fingered hands held at its sides. It looked like something from a science fiction film.
The kind of alien that might step off a flying saucer in a 1950s B movie. But this wasn't fiction. This was a peer-reviewed scientific hypothesis about what dinosaurs might have become if evolution had been allowed to continue. Dale Russell called it the Dinosauroid, and he had built it with his own hands. To understand what Russell was attempting, and why it remains so controversial, we need to understand the man himself. Dale Russell was not a crank. He was not a UFO enthusiast or a fringe theorist. He was one of the most respected vertebrate paleontologists of his generation, a meticulous researcher who had spent his career building the scientific foundation for understanding dinosaur cognition. His specialty was theropod neurology. While other paleontologists were measuring femurs and counting vertebrae, Russell was making endocasts, plaster casts of the interior of dinosaur skulls that revealed the size and shape of their brains. He was mapping the evolution of dinosaur intelligence with a precision that had never been attempted before. And what he found disturbed him. The data showed a clear trend. Across multiple theropod lineages, brain size was increasing over time. Not gradually, exponentially. The rate of encephalization in late Cretaceous theropods was accelerating in a way that suggested something was driving it. Some selective pressure was rewarding bigger brains and rewarding them aggressively. Russell traced this trend through the fossil record, species by species, genus by genus. And when he projected it forward, when he asked what would happen if this trend continued for another 66 million years, the numbers pointed to only one conclusion. Dinosaurs were on track to develop human-level intelligence. Not similar to human intelligence, not approaching human intelligence, equivalent to it. The mathematics were clear. The encephalization quotient of troodontids was increasing at a rate that would have reached human levels within 40 to 50 million years of continued evolution. Factor in the additional time available, the full 66 million years that actually elapsed between the asteroid impact and the present day, and you weren't just looking at human-level intelligence. You were looking at something potentially beyond it. But Russell wasn't content with numbers. He wanted to visualize what such a creature might actually look like. And this is where his project became truly audacious and truly controversial. Working with sculptor Ron Seguin, Russell set out to create a physical model of what he called the Dinosauroid, the hypothetical descendant of Troodon after 66 million years of continued evolution toward higher intelligence. The process was methodical. Russell began with the known anatomy of Troodon and applied a series of evolutionary pressures that he believed would accompany increasing intelligence. First, the brain. A larger brain requires a larger brain case. In mammals, this led to the rounded skull we associate with intelligence, the bulging forehead, the prominent cranium. Russell applied the same logic to his dinosaur descendant, expanding the skull to accommodate a brain 3 times larger than Troodon's original. Second, the posture. Tool use requires free hands. Free hands require upright posture. Russell straightened the Dinosauroid's spine, shifting its center of gravity over its hips in a way that would allow it to walk fully erect. Third, the hands. Sophisticated tool manufacture requires a precision grip. Russell modified the 3-fingered dinosaur hand, giving it greater flexibility and bringing the digits into opposition with each other. Fourth, the eyes. Forward-facing binocular vision is essential for fine manipulation. Troodon already had this, so Russell retained the large forward-facing eyes, though he moved them slightly to accommodate the expanded brain case. The result was a creature that stood about 4.5 feet tall. It had smooth, scaly skin. Its eyes were enormous, with vertical slit pupils. Its hands had 3 fingers plus a partial 4th digit that functioned something like a thumb. It had no external ears. Sound would be channeled through internal structures, as in modern reptiles. And it looked disturbingly human. The Dinosauroid was unveiled at the National Museum of Natural Sciences in Ottawa in 1982. Russell presented it alongside a detailed scientific paper explaining his methodology, his assumptions, and his reasoning. The reaction was immediate, and it was polarized. Some scientists praised Russell's courage in pursuing a thought experiment to its logical conclusion. The Dinosauroid, they argued, was a legitimate exploration of evolutionary possibilities, a way of testing our assumptions about what intelligence requires and how it develops. Others were horrified. The criticism came from multiple directions. Some paleontologists argued that Russell had been too anthropocentric, that he had unconsciously assumed human form was the goal of evolution, and had designed his Dinosauroid to match it. Evolution, they pointed out, has no goal. There's no reason to assume that intelligent dinosaurs would look anything like intelligent mammals. Others objected to the entire premise. Evolution, they argued, is fundamentally unpredictable. You cannot project trends forward over millions of years because you cannot know what selective pressures will apply, what environmental changes will occur, what random mutations will arise. The Dinosauroid wasn't science. It was speculation dressed up in scientific language. Still others raised a more fundamental objection. Even if dinosaurs had survived, even if they had continued evolving larger brains, there was no guarantee they would have developed civilization. Intelligence alone doesn't create technology. It requires a specific combination of cognitive abilities, social structures, and environmental conditions that might never have come together in a dinosaur lineage. Russell listened to all of these criticisms. He acknowledged many of them as valid, but he never retracted the Dinosauroid. Because the criticisms, valid as they were, missed the point of what he was trying to do. Russell wasn't claiming that the Dinosauroid was what dinosaurs would have become. He was exploring what they could have become, and in doing so, he was asking a much deeper question. Why do intelligent beings look the way they do? Is the humanoid form, bilateral symmetry, upright posture, grasping hands, forward-facing eyes, a cosmic accident? A random outcome of primate evolution that could just as easily have gone 1,000 different directions? Or is it something more fundamental, a shape that intelligence requires? This is the question that makes the Dinosauroid so important and so unsettling. Because when Russell applied evolutionary logic to a completely different lineage, starting from completely different ancestors, he ended up with something that looked remarkably similar to us. Not identical. The Dinosauroid retained its reptilian skin, its slit pupils, its 3-fingered hands. It was clearly not human, and clearly not mammalian. But the overall body plan, the architecture of intelligence, was the same. Upright posture, free hands, binocular vision, large brain housed in a rounded skull. Russell had discovered something that many scientists found deeply uncomfortable. the possibility that the humanoid form is not arbitrary, that it might be, in some sense, inevitable. This idea has a name in evolutionary biology: convergent evolution. Convergent evolution is the phenomenon whereby unrelated species independently evolve similar features in response to similar selective pressures. Eyes have evolved independently over 40 times in the history of life. Wings have evolved at least 4 times, in insects, pterosaurs, birds, and bats. Streamlined body shapes have evolved in fish, dolphins, and ichthyosaurs, despite these animals being only distantly related. The logic is simple. Some problems have optimal solutions. If you need to see, you need something like an eye. If you need to fly, you need something like a wing. The laws of physics and chemistry constrain the space of possible solutions, and evolution tends to find the same answers over and over again. Russell was proposing that intelligence might work the same way. If you need to build tools, you need hands that can grasp. If you need to use those hands, you need to free them from locomotion, which means upright posture. If you need to manipulate objects with precision, you need binocular vision. If you need to house a large brain, you need a skull that can accommodate it. These aren't arbitrary requirements. They're engineering constraints, and they point toward a specific body plan: the humanoid body plan. The implications of this idea extend far beyond paleontology. They reach into the heart of one of the oldest questions in human existence. Are we alone in the universe? And if we're not, what do the others look like? For most of human history, we've imagined aliens in our own image. Gods and angels were humanoid. Fairies and demons were humanoid. When science fiction began imagining life on other worlds, it imagined humanoid aliens, sometimes with extra limbs or different skin colors, but fundamentally built on the same body plan as us. Scientists have generally dismissed this as anthropocentrism, the inability to imagine anything different from ourselves. Alien life, they argue, would be truly alien, incomprehensible, built on biological principles we can't even conceive of. But Russell's Dinosauroid suggests another possibility. What if the humanoid form isn't anthropocentrism at all? What if it's physics? What if any creature, anywhere in the universe that evolves high intelligence, will tend to converge on the same basic body plan? Not because evolution has a goal, but because the engineering requirements of intelligence constrain the solution space. This is the hypothesis of convergent intelligence, and it has profound implications for the search for extraterrestrial life. If convergent intelligence is real, then the galaxy might be filled with beings that are, in broad strokes, recognizable to us. Not humans, not even mammals, but humanoid, bilaterally symmetric, upright, tool-using, recognizable as people in a way that a sentient gas cloud or a hive-mind fungus would not be. It would mean that Star Trek got it right by accident, and it would mean that the Dinosauroid, that strange, haunting sculpture in the Ottawa Museum, is more than a thought experiment. It's a window into the shape of minds throughout the cosmos. But we're getting ahead of ourselves, because before we can explore what dinosaur civilization might have looked like, before we can ask whether the Dinosauroid would have built cities and developed science and reached for the stars, we need to answer a more fundamental question. We need to understand why intelligence evolves at all. What is it about the brain, that expensive, fragile, energy-hungry organ, that makes it worth the evolutionary investment? Why did Troodon develop the largest brain of any dinosaur? Why were the troodontids, of all the thousands of dinosaur species, the ones pushing toward higher cognition? The answer lies in a concept that evolutionary biologists call the cognitive niche. And it explains not just why Troodon was getting smarter, but why, given enough time, some descendant of Troodon might have become smart enough to look up at the night sky and wonder about its place in the universe. That story begins in the forests of Cretaceous North America, 75 million years ago, where a small predator was learning to solve problems that no dinosaur had ever solved before. And the solutions it found would change everything. The cognitive niche. Why brains get bigger. 75 million years ago, in what is now Alberta, Canada, a troodon faced a problem that would have killed any other dinosaur. Winter was coming. Not the mild seasonal cooling that most Cretaceous creatures experienced. The polar regions of the late Cretaceous were warm by modern standards, but they still had one feature that made them deadly: darkness. For months at a time, the sun barely rose above the horizon. Temperatures dropped. Prey became scarce. Most dinosaurs dealt with this by migration. They simply walked south until conditions improved. But Troodon stayed. We know this from the fossil record. Troodon remains have been found at latitudes that would have experienced months of near-total darkness during the Cretaceous winter. This wasn't an accident of preservation or post-mortem transport. Multiple specimens, including nesting sites, confirm that Troodon was a year-round resident of these harsh northern environments. This presents an evolutionary puzzle. Why would a small predator choose to remain in an environment where survival was so difficult? Why not migrate like everyone else? The answer lies in Troodon's eyes. Those enormous, forward-facing eyes weren't just for hunting in daylight. Detailed analysis of Troodon's eye sockets reveals something remarkable. The size and shape of the sclerotic ring, the bony structure that supported the eye, indicates that Troodon had exceptional low-light vision. This wasn't an accident. This was an adaptation. Troodon had evolved to hunt in darkness. Think about what this means. In an ecosystem where most predators were effectively blind at night, Troodon could continue hunting. When the sun set and the great theropods bedded down, Troodon's day was just beginning. It had access to an entire temporal niche that was unavailable to its competitors. But hunting in darkness requires more than just good eyes. It requires a different kind of intelligence. During the day, a predator can rely on straightforward pursuit. You see prey, you chase prey, you catch prey. The cognitive demands are relatively simple: pattern recognition, motor coordination, burst speed. Night hunting is different. In low light, you can't always see your prey directly. You have to infer where it is from indirect cues: a rustle in the underbrush, a scent on the wind, the heat signature of a warm body against cold ground. You have to build a mental model of your environment and update it constantly with fragmentary information. This is called inferential reasoning, and it's one of the foundational cognitive skills that separates intelligent animals from merely successful ones. Troodon didn't just see in the dark, it thought in the dark. But darkness wasn't the only pressure pushing Troodon toward higher intelligence. The late Cretaceous was an era of unprecedented ecological complexity, and Troodon was right in the middle of it. Consider the competition. The forests of Cretaceous North America were home to dozens of predator species, each specialized for a particular prey type or hunting strategy. Tyrannosaurs dominated the large game hunting niche. Dromaeosaurs, the raptors of popular imagination, were specialist pack hunters. Ornithomimids were fast pursuit predators. Oviraptorids were specialized nest raiders. Into this crowded landscape, Troodon carved out an unusual niche: generalist opportunist. Stomach contents and toothwear patterns tell us that Troodon ate almost anything: small mammals, lizards, insects, eggs, carrion, perhaps even plant material when prey was scarce. This dietary flexibility was unusual among theropods, which tended toward specialization. And dietary flexibility requires cognitive flexibility. A specialist predator can afford to be stupid. If you only eat one thing, you only need to know one hunting strategy. Your behavior can be largely instinctive, hardwired patterns that activate in response to specific stimuli. A generalist can't work that way. Each food source requires different detection methods, different pursuit strategies, different handling techniques. A generalist must be able to switch between strategies depending on circumstances. It must be able to learn new approaches and abandon old ones that aren't working. In cognitive science, this is called behavioral flexibility, and it's strongly correlated with brain size across virtually all animal lineages. Troodon wasn't just smart for a dinosaur. It was smart because it had to be. Its ecological niche demanded intelligence in a way that few other niches did. But here's where the story gets interesting. Because intelligence, once it starts evolving, creates the conditions for more intelligence. This is called the cognitive ratchet. And understanding it is essential to understanding why Troodon, and potentially its descendants, might have been on an escalator towards sapience. The cognitive ratchet works like this. A slightly smarter individual has a survival advantage. It finds food more efficiently. It avoids predators more successfully. It attracts more mates. So it has more offspring, and those offspring inherit its slightly larger brain. But now the population as a whole is slightly smarter. The competition has increased. The individual who was smart enough to succeed in the previous generation is now merely average. To maintain its advantage, the next generation must be smarter still. This creates an arms race, not against other species, but against members of your own species. The selective pressure for intelligence becomes self-reinforcing. Each generation pushes the next toward higher cognitive capacity. We see this pattern clearly in primate evolution. The most plausible explanation for the explosive growth of the human brain over the past 2 million years is social competition. The need to navigate increasingly complex social relationships, to form alliances, to deceive rivals, to detect deception in others. But social competition requires a specific kind of social structure. It requires groups that are stable enough for relationships to matter, but competitive enough for those relationships to require cognitive effort to maintain. Troodon had exactly this kind of social structure. The evidence for Troodon's social behavior comes from multiple sources. First, the nesting sites. Troodon nests have been found in clusters, suggesting communal nesting grounds similar to modern seabird colonies. This indicates that Troodon tolerated, and perhaps benefited from, the presence of conspecifics during the vulnerable breeding season. Second, the parental care. Troodon eggs show evidence of sophisticated incubation behavior. Adults sat on nests in a specific position, with eggs arranged in a ring beneath their bodies. This brooding posture required careful attention to egg placement and body positioning, cognitive tasks that go beyond simple instinct. Third, the ontogeny. Studies of Troodon growth patterns reveal that juveniles remain dependent on adults for an extended period. Unlike many dinosaurs, which were essentially self-sufficient from hatching, young Troodon required parental care and provisioning for months after emerging from the egg. Extended juvenile dependency is one of the most reliable predictors of intelligence across the animal kingdom. It serves two functions. It allows the brain more time to develop before the individual must fend for itself, and it creates opportunities for learning. Because learning, social learning in particular, is the key that unlocks the door to cumulative culture. Here's a thought experiment. Imagine you're a young Troodon, 75 million years ago. You hatch in a communal nesting ground, surrounded by other hatchlings and watchful adults. Your mother brings you food, small lizards, insects, the occasional mammal. But she doesn't just drop the food and leave. She demonstrates how to handle it, how to kill it efficiently, how to avoid the defensive spines on certain prey species. You watch, you imitate, you learn. As you grow, you begin to follow your mother on hunting expeditions. You observe her techniques, how she moves through the underbrush, how she uses her low-light vision to spot prey in the shadows, how she times her attacks. You practice these techniques yourself, clumsily at first, then with increasing skill. This is social learning, and it's fundamentally different from individual learning. Individual learning is expensive. Every skill must be acquired through personal trial and error. Many of those trials are fatal. You learn that certain prey fights back, that certain berries are poisonous, that certain territories are defended by experiencing the consequences directly. Social learning is cheap. You acquire the accumulated wisdom of your parents without paying the costs they paid to acquire it. Their mistakes become your shortcuts. Their discoveries become your inheritance. And here's the crucial point. Social learning is cumulative. Your mother didn't invent her hunting techniques from scratch. She learned them from her mother, who learned them from her mother, going back generations. Each generation added small improvements, a slightly more efficient technique, a better way to handle a particular prey species. Over time, these improvements accumulated into a body of knowledge far more sophisticated than any individual could develop alone. This is the foundation of culture. And culture, once it gets started, has the same ratcheting effect as cognitive arms races. Each generation inherits a more complex cultural toolkit, which creates pressure for larger brains to handle that complexity, which enables even more complex cultural development. The cognitive ratchet and the cultural ratchet reinforce each other. Together, they create an accelerating feedback loop that, given enough time, can produce something unprecedented. Intelligence that can reflect on itself. We don't know how far troodontids progressed along this path before the asteroid ended their journey. The fossil record from the final 11 million years of the Cretaceous is frustratingly sparse for small theropods. Their delicate bones rarely preserve, and the geological formations from this period are poorly represented. But we can make educated inferences based on evolutionary trajectories.
The encephalization quotient of troodontids was increasing at a rate of approximately 0.02 units per million years during the period for which we have good fossil evidence. If this rate continued, and there's no reason to think it wouldn't have, then by the end of the Cretaceous, troodontids would have achieved an EQ of approximately 6. For comparison, modern crows have an EQ of around 2.5. Chimpanzees are at 2.3. Dolphins reach 4.5. An EQ of 6 would have made late Cretaceous troodontids the most intelligent animals on Earth by a significant margin. Not human level, we're at 7.5, but well beyond anything else that existed at the time. And this is before 66 million additional years of evolution. Let's do the math. The human lineage achieved an EQ increase of approximately 5 units over the past 7 million years, from roughly 2.5 in early hominins to 7.5 in modern Homo sapiens. That's an average rate of about 0.7 units per million years. If troodontids maintained even half that rate, 0.35 units per million years, they would have achieved human-level encephalization within 15 million years of the asteroid impact. 15 million years. That would still leave 51 million years for whatever came next. 51 million years of evolution beyond human-level intelligence. Try to imagine what that means. Try to conceive of a mind that has had 50 million years to develop beyond our current level. A mind that relates to us the way we relate to Australopithecus. We can't imagine it. Our brains literally don't have the capacity to conceive of what that kind of intelligence would be like. It would be as far beyond our comprehension as calculus is beyond the comprehension of a chimpanzee. But here's the thing. This isn't speculation about some hypothetical alien civilization on a distant world. This is what might have happened right here on Earth. This is the future that was canceled by a random rock falling from space. The Troodon mother teaching her chicks on that ordinary Tuesday afternoon wasn't just a dinosaur. She was the ancestor of gods. But evolution doesn't move in straight lines. Intelligence isn't inevitable just because it's possible. The path from Troodon to a technological civilization would have required more than just bigger brains. It would have required the right environmental conditions, the right social pressures, the right sequence of adaptations building on each other in the right order. And most importantly, it would have required something that we're only beginning to understand. It would have required language. Because without language, without the ability to encode complex thoughts into transmittable symbols, cultural evolution hits a ceiling. Knowledge can be demonstrated, but it can't be explained. Skills can be imitated, but principles can't be taught. Each generation must rediscover the reasoning behind inherited techniques, and that rediscovery process limits how complex those techniques can become. Language breaks through this ceiling. Language allows abstract concepts to be transmitted directly from mind to mind. It allows reasoning to be shared, not just results. It allows culture to become truly cumulative in a way that non-linguistic culture cannot. The question is, could dinosaurs have developed language? The answer is more complicated and more hopeful than you might think, because the evidence suggests that dinosaurs were already communicating in ways far more sophisticated than we ever imagined, and the troodontids were leading the way. The lizards, communication and the path to language. In 1995, a paleontologist named Phil Currie made a discovery that would force scientists to completely rethink what dinosaurs sounded like. For over a century, the popular imagination had filled dinosaur films and documentaries with roars, the deep, thundering bellows of predators, and the trumpeting cries of herbivores. These sounds were based on nothing. They were invented by sound designers who needed something dramatic, and they borrowed liberally from modern animals, lions, elephants, crocodiles. But Currie had found something that would change everything. He had found a Parasaurolophus skull with its crest intact.
and that crest was hollow. Parasaurolophus was a hadrosaur, one of the duck-billed dinosaurs that dominated the late Cretaceous landscape. It was a herbivore, about 30 feet long, weighing around 3 tons, and it had a feature that had puzzled paleontologists for decades: a long, curved crest that swept backward from its skull like a trombone. Previous theories had suggested the crest was used for combat or for display, or as a snorkel for underwater feeding. All of these theories had problems. The crest was too fragile for combat. Display structures don't need internal cavities. And the crest didn't connect to the respiratory system in a way that would allow breathing underwater. Curry's team took a different approach. They CT scanned the skull and created a detailed 3-dimensional model of the internal structure. What they found was astonishing. The crest was a resonating chamber. Air passages looped through the entire length of the crest in a complex pattern that could only have one purpose: to modify sound. The crest was, in effect, a biological trombone, a structure designed to amplify and modulate vocalizations. Using the CT scan data, researchers created a digital reconstruction of the Parasaurolophus vocal system and modeled what sounds it could have produced. The results were haunting. Parasaurolophus could produce low-frequency calls that would have carried for miles across the Cretaceous landscape. The sounds were deep and resonant, more like the calls of elephants than the roars of Hollywood dinosaurs. And here's the remarkable part. The exact frequency of the call was determined by the size and shape of the crest. Different species of hadrosaurs had differently shaped crests. Lambeosaurus had a hatchet-shaped crest. Corythosaurus had a rounded helmet. Each would have produced a distinct vocal signature, a species-specific call that allowed individuals to identify their own kind across vast distances. But within species, there was variation too. Juvenile crests were smaller than adult crests, producing higher-pitched calls. Males and females may have had subtly different crest shapes. Each individual would have had a slightly different voice. Hadrosaurs weren't just making noise, they were communicating. They had evolved biological structures specifically designed to transmit complex acoustic information across their social groups. And this was just the beginning. The hadrosaur discovery opened floodgates. Suddenly, paleontologists were looking at dinosaur anatomy with new eyes, searching for evidence of vocal communication that had been overlooked for a century. They found it everywhere. Titanosaurs, the largest animals ever to walk the earth, had internal air chambers in their vertebrae that would have resonated with their vocalizations, potentially producing sounds that could be felt as much as heard. Imagine standing near a creature the size of a building as it called to its herd. The ground would have trembled. Your bones would have vibrated. Ankylosaurs had complex nasal passages that recent analysis suggests could have modulated airflow to produce a range of sounds. Their armor wasn't just for defense. The hollow chambers within it may have functioned as resonating structures. Even Tyrannosaurus rex, the most studied dinosaur in history, is being reconsidered. The latest research suggests that T-Rex may not have roared at all. Its closest living relatives, birds and crocodilians, produce closed-mouth vocalizations, low-frequency rumbles and booms that they generate without opening their jaws. A T-Rex roar may have been more like the subsonic boom of a bittern or the threatening rumble of an alligator. But all of these discoveries, remarkable as they are, pale in comparison to what we've learned about theropod communication. Because theropods didn't just vocalize. They may have been on the path to something far more sophisticated. The key lies in a structure called the syrinx. In modern birds, the syrinx is the vocal organ, the equivalent of our larynx, but far more complex. While the mammalian larynx can produce a limited range of sounds, the avian syrinx can generate an extraordinary variety of vocalizations. This is why birds can sing such complex songs, why parrots can mimic human speech, why crows can produce an astonishing repertoire of calls with distinct meanings. The syrinx is located at the base of the trachea, where it splits into the two bronchi. It's made of modified cartilage rings surrounded by specialized muscles that can change the tension and shape of membranes within the structure, allowing birds to produce multiple independent tones simultaneously. For a long time, scientists assumed the syrinx was a relatively recent evolution, something that appeared after birds split from other theropods. The implication was that non-avian dinosaurs lacked this sophisticated vocal apparatus and were limited to simpler sounds. Then, in 2016, everything changed. A team of researchers studying a 66-million-year-old Vagavus fossil, an ancient bird from Antarctica, discovered a preserved syrinx. It was the first syrinx ever found in the fossil record, and its presence in a bird from the very end of the Cretaceous proved that the structure had evolved before the extinction event. But how long before? Phylogenetic analysis suggests that the syrinx evolved deep in the theropod family tree, possibly as far back as the common ancestor of all Coelurosaurs. This would mean that sophisticated vocal apparatus wasn't limited to birds and their immediate ancestors. It would mean that many theropod lineages, including the troodontids, may have possessed the biological equipment for complex vocalization. The implications are staggering. Troodon may have been able to produce bird-like calls, complex, modulated, information-rich vocalizations that went far beyond simple alarm calls or mating displays. Troodon may have been able to talk. Not language, not yet, but the foundation for language. Understanding the distinction is crucial. Language isn't just complex communication. Many animals communicate in complex ways without having anything like language. Vervet monkeys have distinct alarm calls for different predators, one for eagles, one for leopards, one for snakes. Prairie dogs can encode information about the size, shape, and color of approaching threats into their alarm calls. Dolphins use signature whistles that function as names. None of this is language. Language requires something more: syntax, the ability to combine meaningful units, words or word-like elements, in rule-governed ways to create an infinite variety of novel meanings. Dog bites man means something different from man bites dog, even though the individual words are the same. The order matters. The structure carries meaning. This combinatorial property is what makes language so powerful. With a finite set of words and a finite set of rules, you can express an infinite range of ideas. You can talk about things that aren't present, things that don't exist, things that might happen in the future, things that happened in the past. You can construct hypotheticals, imagine alternatives, plan for contingencies. Syntax is the key that unlocks abstract thought. And syntax requires a specific kind of cognitive architecture. The brain structures that support language in humans are remarkably well understood. Two regions are particularly important: Broca's area, which handles the production of grammatical speech, and Wernicke's area, which handles comprehension. These regions are located in the left hemisphere of the cerebral cortex, and they're connected by a bundle of nerve fibers called the arcuate fasciculus. Damage to any of these structures produces specific, predictable language deficits. Damage to Broca's area produces halting, effortful speech with simplified grammar. Damage to Wernicke's area produces fluent but meaningless speech. Word salad that follows grammatical rules but conveys no coherent meaning. For a long time, scientists assumed these structures were unique to humans, that they had evolved specifically for language in our lineage and had no equivalent in other animals. This assumption was wrong. Research over the past 2 decades has revealed that the neural circuits underlying language are not unique to humans. They're not even unique to primates. Homologous structures have been found in songbirds, in parrots, in corvids. Birds that learn their vocalizations, as opposed to birds whose calls are entirely instinctive, have brain regions that are functionally and structurally similar to Broca's and Wernicke's areas. They have circuits for vocal learning, for combining learned elements into sequences, for understanding the sequences produced by others. The basic neural architecture for language-like communication existed in the dinosaur lineage. It existed in theropods. It almost certainly existed in Troodon. So we have a creature, Troodon, with the cognitive capacity for complex thought, the social structures that would reward communication, the vocal apparatus to produce sophisticated sounds, and the neural architecture to learn and combine those sounds into meaningful sequences. Was Troodon talking? Probably not in any sense we would recognize, but it may have been doing something that occupies the vast middle ground between simple animal communication and true language. Consider what we know about corvid communication: crows, ravens, and their relatives. Corvids have encephalization quotients similar to what we estimate for late Cretaceous troodontids. They live in complex social groups. They use tools. They solve problems. And they have communication systems of remarkable sophistication. Crows have distinct calls for different predators. They have calls that convey emotional states. They have calls that seem to function as names for specific individuals. They can learn new vocalizations throughout their lives, and they can modify their calls based on context, producing different variants for different audiences. Most intriguingly, corvids appear to have something like referential communication. They can direct the attention of other crows towards specific objects or locations. They can point with their calls, indicating not just that something is present, but what that something is and where it can be found. This isn't language, but it's on the road to language. Now give this system 66 million years to evolve. The evolution of language in humans took somewhere between 2 and 6 million years, depending on how you define language and where you draw the starting line. The selective pressures that drove this evolution were primarily social: the need to coordinate group activities, to share information about resources and threats, to maintain alliances and detect defection. Troodon faced identical pressures. Living in social groups, hunting cooperatively, raising young communally. All of these activities benefit from information sharing. The individual who can communicate more effectively has an advantage. Natural selection rewards better communication, which creates pressure for more sophisticated vocal apparatus, larger vocal learning circuits in the brain, more complex social cognition. And here's the ratchet. More complex communication enables more complex social structures, which create even stronger selective pressure for communication. Language and society co-evolve, each driving the development of the other. The human path from simple vocalization to complex language took roughly 3 million years. That's our best estimate for the time between the emergence of Homo erectus, who probably had some form of proto-language, and the appearance of anatomically modern Homo sapiens,
with fully developed language capacity. 3 million years. Troodontids had 66 million years available to them, 20 times longer than we needed. The question isn't whether dinosaurs could have evolved language. The question is whether anything could have stopped them. But language is only the beginning. Language enables something far more powerful: cumulative culture. The ratchet of knowledge that allows each generation to build on the achievements of the previous generation. The engine that transforms clever animals into technological civilizations. And this is where the story gets truly extraordinary. Because once you have language, once you have cumulative culture, you have the raw materials for a feedback loop that can transform a planet. You have the raw materials for fire. Not fire as a natural phenomenon. Dinosaurs certainly knew fire. Lightning storms ignited wildfires throughout the Mesozoic. Dinosaurs evolved in a world shaped by fire, adapted to fire, survived fire. But fire as a tool, fire as something created deliberately, controlled, used. Fire that cooks food and hardens wood and smelts metal and powers engines. Fire that changes everything. Could dinosaurs have mastered fire? Could they have made the leap from intelligent animal to technological species? The answer is more complex than you might think. Because fire isn't just a matter of intelligence. It's a matter of anatomy, ecology, and luck. And the Troodontids had advantages and disadvantages that would have shaped their technological path in ways very different from our own. The fire that never burned. Technology without thumbs. There is a moment in the history of every technological civilization, if such civilizations are common in the universe, when everything changes. A threshold is crossed, a barrier is broken, and the species that crosses it is never the same again. For humans, that moment was fire. Not the discovery of fire. Every animal that lived through a forest fire discovered fire. The moment that mattered was when our ancestors stopped running from flames and started creating them. Controlled fire changed everything. It extended the day beyond sunset. It made inedible foods edible. It provided protection from predators. It enabled migration into cold climates. It hardened wooden tools and eventually smelted metal ones. But more than any of these practical benefits, fire changed how we think. Sitting around a campfire, early humans had something they had never had before: leisure time. Time to talk. Time to plan. Time to tell stories. The campfire became the first classroom, the first laboratory, the first theater. It was the crucible in which culture was forged. So when we ask whether dinosaurs could have developed technology, we are really asking, could they have mastered fire? And the answer is not what you might expect. The standard objection goes like this: dinosaurs couldn't use fire because they couldn't manipulate it. They lacked hands. They lacked opposable thumbs. They couldn't grip a burning stick or arrange kindling or strike sparks from flint. This objection sounds reasonable. It feels intuitive, and it is almost entirely wrong. Let's start with the hands. Troodon's forelimbs ended in three-fingered hands with a significant degree of manual dexterity. The first finger, the equivalent of our thumb, was partially opposable. It could move independently of the other fingers, allowing for a crude but functional grip. More importantly, the wrist structure of Troodontids was remarkably flexible.
CT scans of fossilized forelimb bones reveal a range of motion that exceeded most other theropods. Troodon could rotate its hands inward, bringing the palms toward each other in a position that would allow holding and manipulating objects. Could Troodon have held a burning stick? Almost certainly yes. Could Troodon have arranged kindling into a fire structure? Probably yes. Could Troodon have struck sparks from flint? This is less clear. The precision required for flint knapping is considerable, and we don't know if Troodon's hands were quite up to the task. But here's the thing. Flint knapping isn't the only way to start a fire. Early humans used multiple fire-starting techniques. Flint and steel is actually a relatively late development. The oldest methods involved friction, rubbing sticks together, using a bow drill, spinning a wooden rod against a fireboard. These techniques require dexterity, but not necessarily the kind of fine precision grip that flint knapping demands. They require sustained pressure, rotational motion, and patience. A creature with 3 flexible fingers and a partially opposable first digit could potentially manage them. But there's an even simpler method: fire preservation. Before humans learned to create fire reliably, they learned to keep it alive.
A natural fire, from lightning, volcanic activity, or spontaneous combustion of organic material, could be captured and maintained for extended periods. Coals could be carried in clay-lined containers or wrapped in insulating materials. A single lightning strike could provide a community with fire for years. Fire preservation requires much less manual dexterity than fire creation. It requires the cognitive capacity to understand that fire is useful, the foresight to capture it when it appears, and the social organization to maintain it collectively. Troodon had all of these capabilities. The barrier to dinosaur fire use wasn't anatomical. It was something else entirely. The real obstacle was atmospheric. The late Cretaceous atmosphere was different from our own in ways that would have profoundly affected fire behavior. Most importantly, oxygen levels were higher, possibly as high as 30%, compared to 21% today. High oxygen sounds like it would make fire easier, and in some ways it does. Fires start more readily in oxygen-rich environments. Materials that barely smolder today would have burned fiercely in the Cretaceous. But high oxygen is a double-edged sword. In an oxygen-rich environment, fires are harder to control. They spread faster, burn hotter, and are more difficult to extinguish. A small cooking fire could become a raging inferno in moments. The margin of error shrinks dramatically. This doesn't make fire use impossible, but it makes it more dangerous. Early fire users would have faced a steeper learning curve, with more fatal mistakes along the way. The transition from opportunistic fire use to controlled fire mastery would have been slower and more costly. But here's the twist. Oxygen levels were dropping throughout the late Cretaceous. By the end of the period, the time when troodontids were at their most cognitively advanced, atmospheric oxygen had fallen to approximately 26% and was continuing to decline. Had the asteroid not intervened, oxygen levels would likely have continued falling toward modern values. Within 10 to 20 million years, the atmosphere would have reached a composition essentially identical to today's. The window for controlled fire was opening, not closing. But let's assume the atmospheric problem was solved. Let's assume troodontid descendants eventually mastered fire in an atmosphere with modern oxygen levels. What would their technology look like? This is where things get interesting. Because the path of technological development isn't predetermined. It depends on the specific capabilities and limitations of the species walking it.
Human technology was shaped by human anatomy. Our hands, with their precision grip and fine motor control, led us toward tool traditions that emphasized delicate manipulation: flint knapping, sewing, writing. Our relatively weak bodies led us toward lever-based technologies and mechanical advantage. Our vulnerability to cold led us toward clothing and shelter. Dinosaur technology would have been shaped by dinosaur anatomy. Troodontid hands, while capable, were not as dexterous as human hands. Fine manipulation would have been more difficult. Technologies requiring extreme precision, the threading of needles, the carving of intricate designs, the assembly of tiny components, would have developed more slowly, if at all. But troodontids had advantages humans lacked. Their beaks, or protobeaks, the keratinous structures that covered the front of their jaws, could have functioned as precision tools in ways that human mouths cannot. Modern birds use their beaks for manipulation tasks of remarkable delicacy. Crows use their beaks to shape and use tools. Parrots can untie complex knots.
The beak is not a clumsy appendage. It is a second pair of hands, in some ways more precise than the first. A technological troodontid would have used its beak and its hands in combination, the way a human uses both hands together. Technologies would have developed that assumed this dual manipulation system. Tools might have been designed to be held in the hands and operated with the beak, or vice versa. The result would have been a technological tradition that looked nothing like human technology, even if it achieved similar outcomes. Consider construction. Human architecture is based on our ability to stack and join materials using our hands. We pile stones. We fit logs together. We drive nails and screws. Our buildings are assemblies of discrete components held together by friction, gravity, or fasteners. Bird architecture is fundamentally different. Birds build nests using their beaks, weaving materials together in complex, interlocking patterns. A well-made bird nest is not an assembly of parts. It is a single, integrated structure, a fabric rather than a construction. The weaving technique distributes stress throughout the entire structure, making it surprisingly strong despite being made of seemingly flimsy materials. Troodontid descendants might have developed a technological tradition based on weaving rather than assembly. Their structures would have been woven from processed plant fibers or, given enough time, synthetic materials. Strong, lightweight, organic-looking constructions that a human engineer would barely recognize as architecture. This isn't speculation. This is extrapolation from known principles of bird construction applied to a hypothetical intelligent species. Now consider metallurgy. Human metallurgy followed a specific progression: copper first, then bronze, then iron, then steel. This progression was dictated by the properties of the metals and the temperatures required to work them. Copper melts at a relatively low temperature and can be cold worked. Bronze is an alloy that's harder than copper, but still workable. Iron requires higher temperatures, but is abundant. Steel requires precise control of carbon content. This progression assumes human hands and human tools. A smith holds metal with tongs, strikes it with a hammer, works it on an anvil. The entire process is built around the precision grip and the swinging arm. Troodontid metallurgy might have followed a different path entirely. With their beaks and three-fingered hands, troodontid smiths might have developed techniques that emphasized bending and folding rather than hammering. Their tools might have been designed for pulling and twisting rather than striking. The metals they favored might have been those most amenable to these manipulation styles. Or they might have skipped traditional metallurgy entirely. Consider, the most advanced bird tool users, the New Caledonian crows, don't work stone or metal. They work plant materials. They craft hooks and probes from twigs and leaves, shaping them with their beaks into surprisingly sophisticated implements. A technological civilization descended from troodontids might have developed organic technology to a degree that humans never imagined. Selective breeding of plants for structural properties, biological engineering of living materials, grown rather than built infrastructure. The Dinosauroid civilization might have been green in ways we are only beginning to understand. But there's a deeper question lurking beneath all of this speculation about fire and tools and architecture. Would dinosaur technology have led to dinosaur science? Technology is not the same as science. You can have sophisticated technology without any theoretical understanding of why it works. For thousands of years, humans made bronze without understanding atomic theory. They bred crops without understanding genetics. They built cathedrals without understanding materials science. Science is something different. Science is systematic investigation of the natural world. It requires not just manipulation of nature, but curiosity about nature. Not just, how do I make this work, but why does this work? And this kind of abstract curiosity might be the rarest thing in the universe. Intelligence doesn't automatically produce science. Most intelligent animals show no interest in understanding the world beyond their immediate practical needs. Crows use tools, but they don't experiment with tool designs out of curiosity. Dolphins have complex social cognition, but they don't investigate the properties of water for the pure sake of knowledge. Even among humans, science is rare. For most of human history, we didn't do science. We had technology, we had culture, we had art and religion and philosophy. But systematic empirical investigation of natural phenomena, the scientific method, appeared only once in one culture a few centuries ago. Some historians argue that science is so unlikely, so contrary to natural human tendencies, that it might never have appeared at all were it not for a specific and unrepeatable sequence of cultural developments in early modern Europe. If this is true, if science is not a natural consequence of intelligence but a cultural fluke, then the question of dinosaur civilization becomes much more uncertain. A species could be intelligent. It could have language, culture, technology. It could build cities and write literature and compose music. But it might never develop the peculiar mindset that asks, why, instead of just how. And without science, there's a ceiling. Without understanding the principles behind technology, you can only optimize, not revolutionize. You can make better bronze, but you can't discover electromagnetism. You can breed faster horses, but you can't invent the internal combustion engine. Would troodontid descendants have developed science? We cannot know, but there's a reason to think they might have. Because of all the traits that distinguish scientific thinkers from non-scientific ones, the most important is one that troodontids possessed in abundance: curiosity. The fossil evidence for troodon curiosity is indirect but compelling. Troodon occupied ecological niches that rewarded exploration and investigation. Its generalist diet meant constantly seeking out new food sources. Its night-hunting lifestyle meant navigating unfamiliar environments with incomplete information. Its social structure meant learning from others and, crucially, trying new approaches when old ones failed. Animals in these niches tend to develop what ethologists call neophilia, attraction to novelty. Instead of avoiding the unfamiliar, they investigate it. Instead of clinging to proven strategies, they experiment with new ones. Neophilia is the psychological foundation of science. The willingness to ask,
what happens if, instead of just, how do I get what I want? Modern corvids, the closest cognitive parallel to troodontids among living animals, display remarkable neophilia. They investigate unfamiliar objects. They experiment with novel tools. They play with things for no obvious practical reason, exploring their properties out of what can only be called curiosity. If troodontids were anything like their corvid analogues, they had the psychological raw material for science. Whether they would have developed the cultural and social structures to channel that curiosity into systematic investigation, that's a question we cannot answer. But the possibility was there. So let's imagine it happened. Let's imagine that troodontid descendants mastered fire, developed technology, discovered science. Let's imagine they built a civilization, not like human civilization, but functionally equivalent. Cities, agriculture, writing, mathematics, engineering. What would that civilization have looked like? How would it have differed from human civilization? And would its members, those distant descendants of the Troodon mother teaching her chicks on that Tuesday afternoon, have looked up at the stars and wondered if they were alone? This is the speculation that Dale Russell began with his Dinosauroid. But we can go further. We can go deeper. We can imagine not just the body of a hypothetical saurian intelligence, but its mind, its culture, its history. And that imagination reveals something profound about the nature of intelligence itself. Cities of scale and feather. Imagining dinosaur civilization. Imagine standing on a hillside 66 million years in an alternate future. Below you sprawls a city unlike anything human minds have ever conceived. There are no right angles, no straight lines, no glass and steel towers reaching toward the sky. Instead, the landscape is covered with structures that seem to grow from the earth itself. Spiraling forms woven from materials you cannot identify. Surfaces that shimmer with iridescent patterns. Openings that suggest doorways but follow no architectural logic you recognize. The inhabitants move through this alien cityscape with a fluid grace that seems almost choreographed. They walk upright on two legs, their bodies covered in fine, hair-like feathers that shift color as they pass through patches of sunlight. Their hands, three-fingered, precise, gesture constantly as they interact, supplementing a complex vocal language with a visual component that human eyes can barely follow. They are not human. They have never seen a human. Humans in this timeline never existed. They are the descendants of Troodon, and they have built a world. This is not fantasy. This is extrapolation. Every element of this imagined civilization can be derived from what we know about troodontid biology, projected forward through 66 million years of cultural and technological evolution. And it reveals something profound about the possibilities inherent in intelligence itself. Let's start with the most basic question. What would dinosaur cities look like? Human cities are products of human bodies. Our streets are sized for human walking pace. Our doorways are shaped for human shoulders. Our stairs are proportioned for human legs. Every element of urban design assumes a bipedal primate approximately 5 to 6 feet tall, with forward-facing eyes and grasping hands. troodontid descendants would have built for different bodies. Adult Dinosauroids, following Russell's projection, would have stood approximately 4 to 5 feet tall, shorter than average humans, but with proportionally longer legs and a more vertical posture. Their visual field would have been different. Larger eyes, positioned slightly more laterally on the skull, would have provided excellent peripheral vision, but a different sense of space than human vision creates. This would have profound implications for architecture. Human buildings create enclosed boxes with flat walls because our eyes naturally segment space into distinct regions. We perceive rooms as natural units of space. But a species with broader peripheral vision might not experience space this way. Their architecture might be more continuous, with spaces flowing into one another rather than being sharply divided. Consider the nesting behavior of modern birds, the closest living relatives of theropods. Birds create structures that are fundamentally different from mammalian dens. They are open above, enclosed on the sides, designed for a creature that surveys its environment constantly rather than retreating into darkness. Dinosauroid architecture might have inherited this preference. Their cities might have been characterized by structures that were roofed but open-sided, or roofed with transparent materials that admitted light. Interior spaces might have been arranged vertically rather than horizontally, with different levels connected by ramps or climbing structures rather than stairs. And the materials. The materials would have been extraordinary. We discussed earlier how troodontid technology might have emphasized weaving over assembly. Let's follow that thread, literally, to its logical conclusion. Human architecture transitioned from organic materials to inorganic ones, from wood and thatch to stone and brick, to steel and concrete. This transition was driven by durability and fire resistance. Inorganic materials don't rot, don't burn easily, and can support larger structures. But this transition came at a cost. Inorganic materials are heavy, rigid, and energetically expensive to produce. A modern skyscraper represents an enormous investment of extracted resources and applied energy. What if there was another path? Modern materials science is increasingly looking at biological structures for inspiration. Spider silk is stronger than steel by weight. Bone is more damage-resistant than concrete. Cellulose nanofibers can create materials with extraordinary properties. We are just beginning to understand how to engineer materials with biological principles. A civilization with 66 million years of development, a civilization whose technological tradition emphasized organic manipulation from the beginning, might have mastered biological materials in ways we can barely imagine. Their buildings might have been grown rather than built. Living structures maintained by engineered organisms, self-healing, self-cleaning, adapting to changing conditions, walls that breathed, roofs that responded to weather, infrastructure that was, in some meaningful sense, alive. This isn't fantasy. This is a logical extrapolation from a different technological starting point. But cities are more than buildings. They are social structures. They are solutions to the problem of how thousands or millions of individuals live together, coordinate activities, resolve conflicts, and build something larger than any individual could achieve alone. Human cities evolved to solve human social problems. We are a species with a particular social psychology, cooperative but competitive, tribal but capable of expanding tribal boundaries,
suspicious of strangers, but capable of building trust through repeated interaction. Dinosauroid social psychology would have been different, and this difference would have shaped every aspect of their civilization. Let's think about what we know. Troodontids were social animals. They lived in groups, raised young communally, and probably cooperated in hunting and defense. But theropod social structures would have been organized around different principles than mammalian ones. Modern birds, again, our best model, display an enormous range of social structures. Some are solitary, some form pair bonds, some live in small family groups, some form huge colonies. The common thread is that avian social structures tend to be more fluid than mammalian ones. Birds form and dissolve associations more readily. They're less likely to form the stable, long-term hierarchies that characterize primate societies. If Dinosauroids inherited this tendency, their cities might have been organized very differently from human cities. Human cities have fixed structures, neighborhoods, districts, property boundaries, addresses. We organize space because we organize relationships geographically. Your neighbors are the people who live near you. Your community is your location. Dinosauroid cities might have been organized around networks rather than locations. Relationships might have been maintained across physical distance, with individuals moving fluidly through urban space while maintaining connections to dispersed social groups. The city might have been less a collection of neighborhoods than a continuous field of social interaction, with physical structures serving as nodes in a network rather than containers for communities. This has implications for everything from governance to economics to family structure. Consider governance. Human political systems evolved to solve human political problems. How do you prevent violence between competing groups? How do you make collective decisions when individuals have conflicting interests? How do you maintain order while allowing freedom? Our solutions, tribes, chiefdoms, kingdoms, democracies, reflect our particular psychology. We respond to charismatic leaders. We form stable coalitions. We categorize people into in-groups and out-groups. Our political systems are built on these tendencies. Dinosauroid political systems might have been unrecognizable to us. A species with more fluid social relationships might not have developed the strong in-group, out-group distinctions that characterize human politics. They might not have had nations in any sense we would recognize. No borders, no ethnic identities, no patriotism. Instead, they might have had overlapping networks of affiliation that shifted constantly as individuals moved and relationships formed and dissolved. Governance in such a society might have been less about territorial control and more about network coordination. Leaders might have been those who could maintain the largest and most influential networks, not those who controlled the most territory. Political power might have been fluid, constantly contested through social maneuvering, rather than concentrated through institutional structures. Or perhaps not. Perhaps the requirements of large-scale coordination would have pushed dinosauroid societies toward structures similar to our own. Perhaps cities and agriculture and complex technology inevitably require hierarchical organization, and dinosauroid civilizations would have converged on political forms similar to human ones, despite starting from different psychological foundations. We cannot know. But the question itself reveals how much of what we consider natural about civilization is actually contingent on the specific psychology of the species that built it. Now let's consider something even more fundamental. How would dinosauroids have thought? Not just what would they have known, but how would they have processed information?
How would they have experienced the world? Would their consciousness have been like ours, or something entirely alien? This is perhaps the deepest question in this entire thought experiment, and it brings us face to face with one of the great mysteries of existence, the nature of mind itself. Human consciousness is shaped by human brains. Our experience of time, space, causation, self, and other, all of these are products of the specific neural architecture that evolution built to solve the problems of being a primate on the African savanna. We experience time as flowing from past to future. We experience space as three-dimensional. We experience ourselves as unified agents with continuous identities. We experience other minds as fundamentally similar to our own. But there's no guarantee that these experiences are universal. They might be contingent features of human neurology that would not be shared by a differently evolved intelligence. Dinosauroid brains would have developed from a different starting point. The ancestral theropod brain was organized differently from the ancestral mammalian brain. Different regions were enlarged. Different connection patterns were established. Even if dinosauroid brains eventually achieved cognitive capabilities equivalent to human brains, they might have achieved them through different neural architectures. And different architectures might produce different experiences. Consider how birds process visual information. Mammals have a visual cortex, a region at the back of the brain that processes information from the eyes. This region has a specific layered structure that develops in a specific way and produces a specific kind of visual experience. Birds don't have a visual cortex. They have a completely different brain structure, the dorsal ventricular ridge, that processes visual information in a completely different way. Yet birds have excellent vision. Some birds have better vision than any mammal. The subjective experience of seeing for a bird might be fundamentally different from the subjective experience of seeing for a human. Not worse, not better, but different in ways that might be impossible for either species to comprehend. Dinosauroid descendants of theropods would have inherited avian-style visual processing, not mammalian style. Their experience of seeing would have been more like a bird's than like a human's. What would that be like? We cannot know. We cannot even imagine it, because our imagination is constrained by our experience, and our experience is constrained by our neurology. But we can say this: a dinosauroid scientist studying the nature of consciousness would have arrived at different conclusions than a human scientist. Not because one would be right and the other wrong, but because they would be investigating different phenomena. Consciousness for a dinosauroid might not even be translatable into human terms. This brings us to a question that philosophers have debated for centuries. Is there one kind of mind, or many? Human philosophy has generally assumed that mind is singular. We speak of the mind as if there's only one kind of thing that minds can be. When we imagine alien intelligences, we imagine them as variations on our own minds, maybe smarter, maybe differently cultured, but fundamentally similar in their basic architecture. The Dinosauroid thought experiment suggests this might be wrong. If intelligence can arise through different evolutionary paths, in different neural architectures, with different sensory experiences and different cognitive structures, then there might be many fundamentally different kinds of mind. Ways of thinking that are not just different in degree from human thought, but different in kind. And these different minds might be mutually incomprehensible. Not because one is smarter than the other, not because they lack shared concepts,
but because they're basic categories of experience. The way they carve up reality, the way they experience time and space and causation and self, might be incommensurable. Human science fiction usually imagines first contact as a communication problem. We and the aliens need to find a shared language. But the deeper problem might be that there is no shared conceptual framework. The aliens might think in ways that cannot be translated into human terms, not because the translation is difficult, but because the source concepts have no human equivalents. The Dinosauroids might have been this kind of alien: intelligent, technological, civilized, but thinking in ways that would have been forever opaque to a human mind. And yet, there's a counter-argument, a reason to think that minds, however differently they're implemented, might converge on similar structures. The universe has a specific structure. It has 3 spatial dimensions. It has causation. It has mathematical regularities that we describe with physics. Any mind that interacts with this universe successfully must in some sense model this structure, must represent space, time, cause, and effect. Perhaps these requirements constrain the space of possible minds. Perhaps any intelligence that survives and builds technology must have certain features: a model of physical space, a concept of causation, a distinction between self and world, a capacity for logical inference. If so, then Dinosauroid minds, however differently implemented, might have converged on structures similar to human minds. Not because they evolved the same neural architecture, but because they evolved to solve the same problems, navigating the same universe, manipulating the same matter, predicting the same physical processes. This is the hypothesis of convergent mentality, and it suggests that if we ever did meet a Dinosauroid, if a portal opened to that alternate timeline and we stood face to face with the descendants of Troodon, we might find more common ground than we expect. We might find that mathematics is universal, that logic is universal, that certain basic categories of thought are not human inventions, but discoveries, features of reality that any intelligent species must eventually encounter. We might find that minds, like bodies, converge on optimal solutions. But we will never know. That timeline doesn't exist. The asteroid didn't miss. And this brings us to the strangest part of this story, the part that forces us to confront not just what might have been, but what actually is. Because the dinosaurs didn't completely disappear. They evolved. They became birds. And in the 66 million years since the asteroid impact, birds have been doing something remarkable. Something that suggests the cognitive potential we've been discussing wasn't just theoretical. Something that suggests the path to dinosaur intelligence might not have ended. It might have just taken a different route. The dinosaurs among us. Birds in the unfinished experiment. You have probably seen a dinosaur today. Perhaps it was perched on a telephone wire outside your window. Perhaps it hopped across your lawn, hunting insects. Perhaps it sat on a branch, singing a song whose complexity would challenge the pattern recognition abilities of a supercomputer. We call them birds. We think of them as separate from dinosaurs. Delicate, small, feathered creatures utterly unlike the terrible lizards of the Mesozoic. We are wrong. Birds are not descendants of dinosaurs in the way that you are a descendant of your grandmother. Birds are not related to dinosaurs the way wolves are related to ancient canids. The relationship is more intimate than that. Birds are dinosaurs. Not metaphorically, not poetically, literally. In the same way that you are a mammal,
a sparrow is a dinosaur. The classification is precise and uncontroversial among paleontologists. Birds are members of the clade Theropoda, subclade Maniraptora, subclade Paraves. They are the only surviving lineage of a group that once included Velociraptor, Deinonychus, and yes, Troodon. The asteroid didn't kill all the dinosaurs. It killed the large dinosaurs, the specialized dinosaurs, the dinosaurs that couldn't hide or adapt quickly enough to a world gone mad. But the small, feathered, flying theropods survived. And in the 66 million years since, they have diversified into over 10,000 species, occupying every continent, every habitat, every ecological niche from Arctic tundra to tropical rainforest. And some of them have been getting very, very smart. The story of bird intelligence is one of the most surprising discoveries in modern biology. For most of the 20th century, scientists assumed birds were essentially biological automatons. Their brains were small. They lacked a neocortex, the brain structure that, in mammals, is associated with higher cognition. Their behavior, impressive as it sometimes appeared, was attributed to instinct. Complex but rigid programs selected over evolutionary time, not genuine intelligence. The phrase bird brain became an insult, meaning stupid, unthinking, incapable of complex cognition. This was spectacularly wrong. The revolution began in the 1990s and accelerated through the 2000s as researchers subjected birds, particularly corvids and parrots, to cognitive tests designed to probe the limits of animal intelligence. The results were shocking. Crows use tools, not just simple tools, but compound tools, implements assembled from multiple parts. New Caledonian crows craft hooks from twigs, bending and trimming them to specific shapes. They use these hooks to extract grubs from holes in logs, a task that requires not just tool use, but tool manufacture. But that's just the beginning. Crows plan for the future. In controlled experiments, they cache food not randomly but strategically, hiding more food when they know they'll be hungry later. They can delay gratification, passing up an immediate reward for a better one in the future. They adjust their caching behavior based on whether other crows are watching, hiding food more carefully when potential thieves are present. Crows understand causation. They can infer hidden mechanisms from observable effects. In one famous experiment, crows watched a box that appeared to produce food when a human entered a nearby room. The crows learned to expect food when the human entered, but crucially, they also showed surprise when food appeared without the human entering. They had inferred a causal relationship and noticed when it was violated. Crows recognize faces. They remember individuals who have threatened them, and they teach their offspring to recognize those individuals. A crow that has never seen you before might attack you because its parents told it you were dangerous. This is cultural transmission of information, exactly the kind of cumulative social learning we identified as essential for the development of civilization. And perhaps most remarkably, crows appear to have something like a theory of mind. Theory of mind is the ability to understand that other individuals have mental states, beliefs, desires, intentions that may differ from your own. It's the cognitive capacity that underlies deception, empathy, cooperation, and communication. It's what allows you to understand that someone might believe something false, or want something you don't want, or plan something you don't expect. For decades, theory of mind was considered uniquely human. Then it was found in great apes, then in dolphins.
Each discovery pushed back the boundaries of what we thought was special about human cognition. The Corvid research pushed those boundaries further than anyone expected. In a series of elegant experiments, researchers demonstrated that ravens understand the visual perspective of other ravens. A raven that has cached food while being watched by another raven will return later to recache the food in a new location, but only if it has itself experienced stealing from another raven's cache. It uses its own experience of theft to predict that others might steal from it. This isn't simple stimulus-response learning. This is modeling the mental states of others based on self-knowledge. This is theory of mind. The implications are profound. Theory of mind evolved independently in birds and mammals. Two lineages separated by over 300 million years of evolution converged on the same cognitive capacity. Why? Because theory of mind is useful. In social species, predicting the behavior of others is crucial for survival. Natural selection rewards individuals who can anticipate what others will do, and the best way to predict behavior is to model the minds that generate it. Convergent evolution again. The same problem, navigating complex social environments, produces the same solution across vastly different lineages. But corvids aren't the only intelligent birds, and the breadth of avian intelligence suggests something even more remarkable than convergent evolution. It suggests that the theropod brain, the dinosaur brain, was pre-adapted for intelligence in ways we're only beginning to understand. Parrots rival corvids in cognitive tests. They can learn hundreds of words and use them meaningfully, not just as conditioned responses. The famous African gray parrot Alex could identify 50 different objects, 7 colors, 5 shapes, and quantities up to 6. He could answer questions about objects' properties, express preferences, and even ask questions himself. Alex wasn't trained to ask questions. He spontaneously began asking, "What color?" when shown novel objects. He had learned the concept of question asking from watching researchers query each other, and he generalized it to his own curiosity. Pigeons can learn abstract rules and apply them to novel situations. They can categorize images by concepts like human-made versus natural, with accuracy that rivals human performance. They can learn to distinguish paintings by Monet from paintings by Picasso, and then correctly classify paintings by each artist that they've never seen before. Chickens, often considered among the least intelligent birds, demonstrate numeracy, self-control, and even some evidence of self-awareness. They can anticipate future events based on past experience. They adjust their behavior based on their social status within the flock. The common thread across all these species isn't a single genius lineage. It's the entire bird brain architecture. The dinosaur brain architecture. A neural structure that, despite lacking the mammalian neocortex, is capable of producing intelligence equivalent to that of apes. Different hardware, same software capabilities. How is this possible? The answer lies in the way bird brains are organized, and it overturns everything we thought we knew about the neural requirements for intelligence. Mammalian intelligence is concentrated in the neocortex, the wrinkled outer layer of the brain that expanded dramatically during primate evolution. The neocortex has a specific layered structure, with 6 distinct layers of neurons organized in columns. This architecture was thought to be essential for higher cognition. Birds don't have a neocortex. Their forebrains are organized entirely differently, with clusters of neurons called nuclei, rather than layers and columns. For a long time, scientists assumed this meant birds were fundamentally limited in their cognitive potential. The neocortex was the seat of intelligence. Without it, higher cognition was impossible. Then researchers started looking more carefully at bird brains. What they found was that birds had evolved a completely different neural architecture that accomplished the same functions. The avian pallium, the bird equivalent of the mammalian cortex, is organized differently, but it contains the same types of neurons, the same neurotransmitters, the same basic computational circuits. Birds didn't evolve the neocortex. They evolved something else that works just as well. This discovery has revolutionary implications for our understanding of intelligence. It means that intelligence is not about specific brain structures. It's about computational capacity. And computational capacity can be achieved through multiple architectural paths. The mammalian path is one solution. The dinosaurian path is another. Both work. Both can produce minds capable of reasoning, planning, communicating, and understanding the world. Now consider what this means for our thought experiment. We asked earlier whether troodontids could have evolved human-level intelligence. We speculated about what 66 million years of continued evolution might have produced. But we were asking the wrong question. We don't have to speculate. We can observe. Birds have had 66 million years of evolution since the asteroid impact. And in that time, multiple lineages have independently evolved high intelligence. Corvids, parrots, perhaps others we haven't yet fully investigated. These birds started from a cognitively depleted baseline. The avian ancestors that survived the extinction were not the most intelligent theropods. They were the small, generalized species that could survive the catastrophic conditions of the impact winter, not the large-brained specialists like the troodontids. Yet even starting from this reduced baseline, birds achieved remarkable cognitive heights. Corvid intelligence rivals that of great apes. If the same evolutionary pressures that produced crows had operated on troodontids, on the most intelligent dinosaurs, not the survivors, what might have emerged? The answer is not speculative, it's mathematical. Corvids achieved their current cognitive level in approximately 40 million years of evolution from small Paleocene ancestors. Troodontids were already cognitively superior to those ancestors. They had a 66 million year head start. The troodontid trajectory, uninterrupted, would have reached cognitive heights that we cannot meaningfully imagine. Not just human-level intelligence, not just beyond human intelligence, something so far beyond our conception that we have no words for it. And this isn't fantasy. This is evolutionary logic applied to the fossil record. But here's where the story takes its strangest turn. Because bird evolution isn't finished. The cognitive ratchet is still turning. And some researchers believe we may be witnessing the early stages of another transition toward higher intelligence. This time in the corvids. Crow populations worldwide are adapting to human environments with unprecedented speed. Urban crows have learned to use cars as nutcrackers, dropping walnuts in front of vehicles and waiting for them to crack. They've learned to follow garbage trucks on collection days. They've learned to recognize human uniforms and distinguish between dangerous and harmless people. But more importantly, they're teaching these skills to their offspring. And their offspring are teaching them to their offspring. Cultural evolution is occurring at a pace that far exceeds genetic evolution. Some researchers have speculated that corvids are entering the same cognitive feedback loop that drove human brain evolution 2 million years ago. Social complexity is driving cognitive development, which enables greater social complexity, which drives further cognitive development. If this is true, if corvids are on an evolutionary trajectory toward higher intelligence, then the dinosaur experiment isn't over. It's still running, and we might be alive to see the early results. This raises a question that science fiction has explored, but science has rarely confronted directly. What should we do about it? If corvids are genuinely on a path toward sapience, do we have obligations to them? Should we protect them? Educate them? Leave them alone? These questions might seem absurd. We're talking about crows. They're smart, but they're not people. But neither were troodontids. Neither were the ancestors of Homo sapiens 2 million years ago. Neither, for that matter, were our great-grandparents' ancestors. Intelligence isn't a fixed property. It's a process, a trajectory. And we might be watching that trajectory unfold in real time. The dinosaur civilization we've been imagining throughout this exploration, the cities of scale and feather, the alien minds, the technology we can barely conceive, that civilization might still emerge, not in some alternate timeline, here, on this Earth, in the descendants of the dinosaurs that survived. All it takes is time. But time is exactly what the original dinosaurs didn't have. And this brings us to the cosmic perspective on this entire story. The question of what it means that intelligence almost arose on Earth 66 million years earlier than it did, and the question of what this implies about intelligence elsewhere in the universe. Because if the dinosaur trajectory tells us anything, it tells us that intelligence is not as rare as we might have thought, that the conditions for its emergence are not as stringent as we might have assumed, that the universe might be far more full of minds than we ever dared to imagine. And it raises a question that has haunted astronomers and philosophers for decades, a question that the dinosaur thought experiment transforms from abstract speculation into urgent mystery. If intelligence arises so easily, if it was about to arise on Earth 66 million years ago, then where is everyone else? Why is the galaxy so silent? The Great Silence. Dinosaurs, Fermi, and the Fate of Intelligence. In 1950, the physicist Enrico Fermi sat down to lunch with several colleagues at Los Alamos National Laboratory. The conversation drifted, as conversations among physicists often do, toward the question of extraterrestrial life. Fermi listened as his colleagues discussed the vastness of the universe, the billions of stars, the probability that some fraction of them hosted planets, the likelihood that some fraction of those planets developed life. The numbers seemed overwhelming. The galaxy should be teeming with intelligent civilizations. Then Fermi asked a simple question that has haunted science ever since. Where is everybody? This is the Fermi Paradox. And 66 million years of dinosaur evolution makes it far more troubling than Fermi could have known. Let's walk through the logic carefully. The Milky Way galaxy contains approximately 200 billion stars. Current estimates suggest that most of these stars have planets. Conservative calculations indicate that there are at least 10 billion Earth-like planets in habitable zones, places where liquid water could exist on the surface. The galaxy is approximately 13 billion years old. Our solar system is about 4.5 billion years old.
This means there are star systems that are 8 billion years older than ours. Systems where intelligent life could have emerged when our sun was still a cloud of hydrogen gas. 8 billion years is an incomprehensible span of time. Human civilization has existed for maybe 10,000 years. Scientific civilization has existed for maybe 500. In 8 billion years, a technological species could have colonized the entire galaxy many times over. Even using technology we can already imagine. No faster-than-light travel required. And yet, we see no evidence of galactic civilization. No megastructures around distant stars. No radio signals from other worlds. No probes visiting our solar system. No artifacts on the Moon or Mars. Silence. This silence requires explanation. And the explanations that have been proposed are, without exception, disturbing. The most disturbing explanation is the Great Filter. The Great Filter hypothesis suggests that somewhere between the formation of a habitable planet and the emergence of a galaxy-spanning civilization, there is a barrier, a filter, that almost no species passes through. The question is, where is the filter? If the filter is behind us, if the hard step is the origin of life, or the evolution of complex cells, or some other hurdle that Earth has already passed, then we may be among the first intelligent species in the galaxy. The silence would be explained by the fact that intelligence is extraordinarily rare. But if the filter is ahead of us, if the hard step is something that technological civilizations encounter after they develop, then we are in danger. The silence would be explained by the fact that civilizations destroy themselves before they can spread to the stars. Nuclear war, engineered pandemics, runaway artificial intelligence, climate collapse. The technologies that could save us might be the same technologies that doom us. This is the terrifying interpretation of the Fermi Paradox. Every technological civilization develops the means for its own destruction before developing the means for interstellar travel. And every civilization, given enough time, uses those means. We would not be special. We would just be next. But the dinosaur thought experiment adds a new dimension to this problem, and in some ways it makes the paradox even worse. Consider what we've established throughout this exploration. Troodontids were on an evolutionary trajectory toward high intelligence. They had the cognitive capacity, the social structures, the manipulative abilities, the sensory equipment. Given another 20 to 50 million years, a blink of an eye in geological terms, they might have achieved human-level intelligence or beyond.
This means that intelligent life almost arose on Earth 66 million years before it actually did. If the asteroid had missed, dinosaur civilization might have emerged in the Paleocene. By now, by what would be our now, they would have had 60 million years of technological development beyond the point where we currently stand. 60 million years. Try to comprehend that timescale. Human civilization has existed for 10,000 years. Scientific civilization for 500. The Industrial Revolution was 250 years ago. The Digital Revolution was 50 years ago. In 60 million years, a civilization that started at our current level could have disassembled planets for raw materials, could have reshaped the solar system, could have engineered new forms of life and new forms of mind, could have spread across the galaxy 1,000 times over. The Dinosauroid descendants of Troodon should be everywhere. They should be impossible to miss. Their presence should be as obvious as the sun in the sky. And yet, we're here. They're not. What does this mean? There are several possible interpretations, and none of them are comfortable. The first interpretation:
The asteroid wasn't random. This sounds like conspiracy theory. It sounds like the desperate grasping of minds unable to accept cosmic indifference. But it's worth examining seriously. What if intelligent civilizations, when they arise, tend to prevent the emergence of competitor intelligences in their vicinity? What if there's a kind of cosmic selection against multiple intelligent species on the same planet, or in the same region of the galaxy? We have exactly one data point, Earth. And on Earth, intelligence emerged once, rose to dominance, and has shown an uncomfortable tendency to eliminate other intelligent species. Neanderthals, Denisovans, possibly others we haven't yet discovered. Homo sapiens did not coexist peacefully with its intelligent relatives. What if this pattern scales up? What if the asteroid was not an accident, but an intervention? A deliberate reset by an older civilization that didn't want competition. This is wild speculation. There's no evidence for it. But the Fermi Paradox forces us to consider wild speculations because the conventional explanations don't add up. The second interpretation: intelligence is self-limiting. Perhaps the dinosaur trajectory would not have led to galactic civilization. Perhaps no trajectory does. Consider, every increase in intelligence brings an increase in the capacity for destruction. Stone tools can kill individuals. Bronze weapons can conquer cities. Iron weapons can destroy nations. Nuclear weapons can eliminate civilizations. Biotechnology can threaten species. And we're just getting started. Within the next century, humans will likely develop technologies capable of rendering Earth uninhabitable. Engineered pathogens, self-replicating nanotechnology, artificial superintelligence, climate engineering gone wrong. Any of these could end not just human civilization, but all complex life on Earth. Perhaps every intelligent species faces this gauntlet. Perhaps the period between developing technology and developing wisdom is always dangerous. Perhaps most civilizations, 99%, 99.9%, destroy themselves during this transition. The Dinosauroids, in this interpretation, would have faced the same gauntlet. Their trajectory would have led to the same dangerous technologies, and they would have had the same probability of surviving them, which is to say, almost zero. The third interpretation: we're not looking correctly. Perhaps Dinosauroid civilization did emerge. Perhaps it exists right now, somewhere in the cosmos, 66 million years ahead of us in development. But perhaps we wouldn't recognize it if we saw it. Human SETI, the search for extraterrestrial intelligence, looks for signals that human technology would produce: radio waves, laser pulses, megastructures that block starlight. We're looking for civilizations that are, in essence, a few centuries ahead of us technologically. But a civilization 60 million years ahead might not produce any of these signatures. Consider, 200 years ago, the most advanced civilization on Earth was visible from its fires and its cleared land. 100 years ago, it was visible from its electrical lights. 50 years ago, it was broadcasting radio waves that could be detected across interstellar distances. Today, our radio transmissions are increasingly digital, encrypted, frequency hopping, spread spectrum, invisible to the detection methods that would have worked in 1970. Our energy use is becoming more efficient, not less. Our presence is becoming harder to detect from space, not easier. Extrapolate this trend for 60 million years. A truly advanced civilization might be indistinguishable from nature. Its technology might operate at scales we can't perceive, in the quantum realm, or at the boundaries of black holes, or in dimensions we haven't discovered.
its communication methods might be as invisible to us as radio waves would be to a Roman emperor. The Dinosauroid descendants might be all around us. We might be swimming in their presence, and we would have no way of knowing. The fourth interpretation: something changed. Perhaps the trajectory we've been tracing, from animal intelligence to tool use to technology to civilization to galactic expansion, is not inevitable. Perhaps it's not even common. Perhaps most intelligent species reach a certain point and then stop. Not because they destroy themselves, not because they're destroyed by others, but because they choose a different path. Consider what we know about human happiness. Study after study shows that beyond a certain level of material security, additional technological development does not increase well-being. The citizens of wealthy nations are not proportionally happier than the citizens of moderately prosperous ones. Technological progress creates new problems as fast as it solves old ones. What if most intelligent species, once they've secured their basic survival, decide that galactic expansion isn't worth the effort? What if they turn inward instead of outward, developing rich inner lives, complex cultures, sustainable relationships with their home planets, rather than spreading endlessly across the cosmos? This wouldn't be failure. It wouldn't be extinction. It would be a choice. And if this is the common pattern, if most intelligent species choose contentment over conquest, then the silence would be explained. The galaxy would be full of minds, but those minds would be quiet, content, uninterested in the kind of expansion that would make them visible across interstellar distances. The Dinosauroids, in this interpretation, might be on their home world right now, peaceful, happy, utterly uninterested in us. But there's one more interpretation, and it's perhaps the strangest of all. What if we're wrong about the asteroid? Not about whether it happened. The evidence for the Chicxulub impact is overwhelming, but about what it means. We've been treating the asteroid as a tragedy, an accident, a cosmic catastrophe that ended one potential path for intelligence and, by sheer luck, opened another. But what if it wasn't luck? What if the dinosaur trajectory had a ceiling? What if troodontid evolution was approaching a limit? Some biological or physical constraint that would have prevented them from reaching true sapience? And what if the asteroid, by clearing the ecological stage, created conditions that allowed a different kind of intelligence to emerge? A kind of intelligence that didn't face the same constraints. Mammals evolved differently from dinosaurs. We're warm-blooded in a different way, with higher metabolic rates that demand more energy but enable more sustained cognitive activity. Our brains develop differently, with extended periods of neural plasticity that allow for unprecedented learning capacity. Our social structures are different, with pair bonding and extended families that create intense selection pressure for social cognition. What if these differences matter? What if mammalian intelligence has access to cognitive spaces that saurian intelligence never could have reached? This is not to say that mammals are superior. It's to say that we might be different in ways that matter for the development of technological civilization. The asteroid, in this interpretation, wasn't a tragedy. It was a transition, a cosmic intervention that ended one experiment and began another, an experiment that might have greater potential for long-term success. We cannot know which of these interpretations is correct. We have only one data point: Earth. One emergence of intelligence: us.
One extinction event, the one that killed the dinosaurs and spared our ancestors. But the dinosaur thought experiment forces us to take the Fermi Paradox seriously in a way that abstract probability calculations cannot. Because it shows us that intelligence almost arose here, on this planet, 66 million years before it actually did. That the emergence of minds capable of asking questions about the universe is not a one-time cosmic fluke, but a robust evolutionary tendency. And if it's a robust tendency here, it should be a robust tendency elsewhere. The galaxy should be full of minds. And yet it's silent. This silence is data. It tells us something profound about the nature of intelligence, the fate of civilizations, and our own place in the cosmic story. We just don't know yet what it's telling us. And this brings us to our final chapter. The chapter that turns from the past and the possible to the present and the actual. The chapter that asks what all of this means for us, here, now, on this planet, at this moment in history. Because we are the intelligence that emerged. We are the species that asks these questions. We are the descendants of the small, shrew-like mammals that hid from the dinosaurs and inherited the Earth. And the choices we make, in the next century, in the next few decades, may determine whether the human experiment ends the same way the dinosaur experiment almost did, or whether we become something new, something unprecedented, something that, 66 million years from now, might look back on this moment as the beginning of everything. The inheritors, what the dinosaurs teach us about ourselves. We began this journey 66 million years ago, on an ordinary Tuesday afternoon, watching a Troodon mother teach her chicks to hunt. We've traveled through time and possibility, through the intricate machinery of evolution and the vast silence of the cosmos. We've imagined cities that were never built, minds that never awakened, a future that was erased by a rock falling from space. Now we return to the present, to this moment, to the species that actually inherited the Earth, not through superiority, not through cosmic design, but through the blind luck of being small enough and adaptable enough to survive what nothing else could survive. We are the winners of a lottery we never entered. And the question we must now ask is, what do we do with our winnings? The dinosaur thought experiment is not really about dinosaurs. It's about us. It's about understanding that intelligence is precious precisely because it's precarious. That minds capable of contemplating the universe are not inevitable but contingent, the product of billions of years of evolution, countless extinction events, and a chain of luck so improbable that calculating it would exhaust the mathematics of probability. The troodontids were on their way. They had been evolving for 60 million years. They had developed brains capable of problem-solving, hands capable of manipulation, social structures capable of cultural transmission. Everything was in place. And then a rock fell from the sky. Not because the universe was malevolent, not because fate had other plans, simply because rocks fall from the sky sometimes. And 66 million years ago, one of them happened to hit Earth instead of sailing past into the void. That's it. That's the entire difference between a universe with dinosaur philosophers and a universe with human philosophers. Randomness. If this doesn't fill you with a sense of existential vertigo, you haven't understood it properly. But vertigo is not the only appropriate response. There's another emotion that the dinosaur story should evoke, and it's more important than fear or wonder or cosmic humility. It's responsibility. Because we're here now. We exist. We are the intelligence that emerged from the wreckage of the Cretaceous extinction. And unlike the troodontids, we know what can happen. We know that 66 million years of evolutionary progress can be erased in an afternoon. We know that intelligence, once lost, may never return. The dinosaurs didn't know the asteroid was coming. They couldn't have known. They had no telescopes, no orbital tracking systems, no understanding of celestial mechanics. They lived and died in ignorance of the threat that ended them. We don't have that excuse. We know about asteroids. We've cataloged thousands of near-Earth objects. We've sent spacecraft to study them, even to impact them experimentally. We have the technology today to detect and deflect any asteroid that threatens our planet, if we choose to invest in doing so. The dinosaurs couldn't protect themselves. We can. And if we don't, if we allow ourselves to be destroyed by a threat we understood and could have prevented, we won't be victims. We'll be fools. We'll be the species that knew better and chose not to act. The dinosaurs deserve better successors than that. But asteroids are not the only threat, and in some ways, they're not even the most pressing one. The dinosaurs were killed by a force outside their control. We are more likely to be killed by forces within it. Nuclear weapons, climate change, engineered pandemics, artificial intelligence systems that escape our ability to direct them. These are not cosmic accidents. These are choices. Choices we make as individuals, as nations, as a species. And here's where the dinosaur story becomes not just cautionary, but instructive. Because the troodontids were successful precisely because they were adaptable. They thrived in changing environments. They exploited new ecological opportunities. They responded to challenges with flexibility rather than rigid specialization. The dinosaurs that died, the tyrannosaurs, the sauropods, the hadrosaurs, were specialists. They were exquisitely adapted to their niches, but when those niches disappeared, they had nowhere to go. Their very success had made them vulnerable. Troodontids were different. They were generalists, problem solvers, opportunists. And if they had survived the asteroid, it would have been because of these traits. We share these traits. Humans are the ultimate generalists, capable of living in any environment, exploiting any food source, solving any problem we set our minds to. This is our inheritance from our mammalian ancestors, who survived the extinction precisely because they weren't committed to any single way of life. But we're in danger of losing this flexibility. Modern human civilization is becoming increasingly specialized. Our economic systems optimize for efficiency, which means eliminating redundancy. Our agricultural systems depend on a handful of crop varieties. Our energy systems rely on finite resources extracted from specific locations. Our technological systems concentrate knowledge and capability in smaller and smaller groups of experts. Specialization creates fragility. A supply chain disruption can halt global manufacturing. A single disease can collapse entire industries. A cyber attack can disable critical infrastructure. A financial crisis can cascade through interconnected markets with a speed and severity that no individual actor can control. We've built a civilization of remarkable complexity and capability. But we've also built a civilization that is, in some ways, as vulnerable as the great dinosaurs of the late Cretaceous. The troodontids, if they had built a civilization, might have avoided this trap. Their evolutionary history had selected for flexibility, for distributed networks rather than centralized hierarchies, for generalized capabilities rather than narrow specialization. We have a choice about what kind of civilization we build. We can continue optimizing for efficiency at the cost of resilience. Or we can deliberately cultivate the flexibility that allowed our ancestors to survive when the specialists perished. The dinosaurs can't make this choice. We can. There's another lesson in the dinosaur story, and it's perhaps the most profound of all. Intelligence is not a destination. It's a journey. The troodontids were on a path. They weren't intelligent in the way we are. They didn't have language or writing or mathematics. But they were moving in that direction. Each generation was slightly more capable than the last. Each million years brought new cognitive abilities, new behavioral flexibility, new potential. Then the path ended. We think of ourselves as the end point of evolution, as if the whole history of life on Earth was leading toward Homo sapiens, as if we were the destination and everything else was just the journey. This is an illusion, a comforting illusion, but an illusion nonetheless. We are not the end point. We are on a path too. A path that began with small-brained primates on the African savanna and has led, so far, to cities and science and art and philosophy. But the path doesn't end here. It continues. And the question we face is, where does it go? There are two possible futures for human intelligence. Two paths forward from this moment. The first path is stagnation. We reach some plateau of cognitive capability, perhaps where we are now, perhaps somewhat higher, and we stay there. We continue to exist, but we don't fundamentally change. 1,000,000 years from now, our descendants are still recognizably human, still limited by the same cognitive constraints that limit us. This would not be failure exactly. Survival is not nothing. But it would mean that the great project of intelligence, the expansion of mind into new territories, the development of new ways of thinking and understanding, had reached its end with us. The second path is continuation. We keep moving. We enhance our cognitive capabilities through technology. We merge with artificial intelligence. We edit our genomes to expand our neural capacities. We become something new, something that relates to us the way we relate to Troodon. This is a frightening prospect. It means giving up what we are. It means becoming something we cannot currently imagine. It means stepping into a future that is genuinely unknowable. But consider the alternative. If we stagnate, if we decide that this is as far as intelligence goes, then we are making a cosmic decision on behalf of the entire future of mind in the universe. We are saying that the maximum cognitive capability of Earth-originated life is approximately what Homo sapiens achieved in the 21st century. That seems small. The troodontids were on a path toward intelligence. That path was cut short by chance. If they had survived, they would likely have surpassed us, not because they were better, but because they would have had more time. We have inherited their time. The 66 million years that should have belonged to them now belong to us. The question is whether we will use that time, whether we will continue the journey that began in the neurons of the first animals, accelerated in the brains of early theropods, and was interrupted by cosmic accident, or whether we will stop here, at the beginning of the story, and call it the end. There's one more lesson in the dinosaur thought experiment, and it brings us back to where we started, to that Troodon mother on that ordinary Tuesday afternoon teaching her chicks to hunt. She didn't know she was part of something larger. She didn't know that her lineage had been developing for 100 million years, that her brain was the most sophisticated structure on the planet, that her descendants might have built civilizations and sent spacecraft to the stars. She was just living her life, teaching her children, doing what her instincts and her intelligence told her to do. And that was enough. That was enough to continue the journey. That was enough to push the needle of evolution fractionally forward. That was enough to add her chapter to the story of intelligence on Earth. She didn't need to understand the cosmic significance of her existence. She just needed to live it. We're not so different. We don't know where the journey of intelligence is going. We can't comprehend the minds that might exist 1,000,000 years from now, any more than Troodon could have comprehended us. We are, from the perspective of the far future, primitives, early chapters in a story whose ending we cannot imagine. But we can do what the Troodon mother did. We can live our lives. We can teach our children. We can push the needle forward. Not because we understand the destination, because the journey itself is the meaning. 66 million years ago, an asteroid fell from the sky and erased a future that was already taking shape in the neurons and behaviors and social structures of a species we would never meet. That future is gone. It can never be recovered. The Dinosauroid civilizations, the Saurian philosophers, the theropod scientists gazing at the stars, they exist only in our imagination, ghosts of a possibility that was never realized. But something else happened in those 66 million years, something unexpected. In the wreckage of the Cretaceous world, in the ash and the darkness and the long nuclear winter, a small furry creature crawled out of its burrow and looked up at a sky that was finally clearing. It was cold. It was hungry. It had no idea what had happened or what would come next. But it was alive, and in its tiny mammalian brain there was a spark, a capacity for learning, for adapting, for solving problems that would, over millions of years, grow into something remarkable. We are the descendants of that creature. We carry its legacy in every neuron, every heartbeat, every thought. And we carry another legacy too, the legacy of the dinosaurs who almost became what we became. The legacy of the troodontids who were on their way to intelligence when the sky fell. They didn't make it, but in some strange way, their story continues in us. We are not their descendants, but we are their inheritors. We have taken up the journey they began. We are asking the questions they would have asked. We are looking at the same stars they would have looked at, wondering the same things they would have wondered. The Troodon mother never got to see what her lineage might have become. But if she could see us, if she could somehow understand what emerged from the ruins of her world, perhaps she would recognize something. Perhaps she would see, in our curiosity, in our tool-making, in the way we teach our children and care for our families, an echo of herself. Perhaps she would understand that intelligence is not a species or a lineage. It's a flame. And as long as the flame is carried, by feathered hands or furry ones, by scales or by skin, the journey continues. The asteroid missed. Not the one that fell 66 million years ago, the one that almost fell today, the one that didn't strike because we saw it coming and chose to prevent it.
The one that didn't end our story because we decided our story wasn't finished yet. This is the gift the dinosaurs gave us. Not by intention, but by example. They showed us what can be lost. Now it's up to us to show the universe what can be saved, what can be built, what can be become.
The Troodon mother finished her lesson 66 million years ago, never knowing it was the last lesson her lineage would teach. But we heard it anyway. We heard it in the fossil record, in the bones and the teeth and the shapes of ancient skulls. We heard it in the silence of the stars and the depths of the question, why us? Why now? Why at all? And we're still listening. We're still learning. We're still on the journey she began. And the lesson, finally, is this. We are not the destination. We are the next step. And the path goes on. The end.